Hi, this is the video solution of GATE 25 Mathematics question number 44. This question related to question space, and this is a mark 2 question. That means more than one option may be correct. So we need to check all options individually. Okay. So let's see the question first. So question reads as follows. We consider the Euclidean spaces, and here we have given to the unit sphere. This is what? This is unit sphere. Okay. And in the unit sphere, there's a relation x1, x2, x3, and another y1, y2, y3 related if and all of the last coordinates are same. Okay. Now, we are denoting the quotient space to be by capital X and L be the quotient map. Okay. Sending the point x1, x2, xn to it's the equivalence class. So that means this third bracket x1, x2, xn represent a point the quotient space. Okay. Now the question is that, of course, nevertheless, x is given to the quotient topology. Now the question is that x is homeomorphic to which one of these following options. So we need to check that. Okay. So so before solving the problem, let me show you the NPTEL University course references which can be used for solving this problem, so that you can see those lectures as a purpose study materials. Okay. The NPTEL University course reference. This course is residence topology. This is taken from the SF theory and IIT Mazatlan with faculty. And the lecture 23, the named as the quotient topology, and the YouTube link is given, so you can directly go and watch the video. Okay. And okay, now before solving the problem, let me give a quick recap of the useful definitions and theorems. Okay. So first definition is the quotient topology. So that means we have some equals relation tilde, and we have some quotient is x by tilde, and then we have the corresponding quotient of L from x to x, as such that x goes to third bracket is continuous. So we are giving a topology on x such that with respect to the topology, the quotient map becomes continuous. So that topology is known as the quotient topology. Okay. So there is a definition of quotient topology. I understand this is a very basic common thing, but for the sake of completeness, I am just put the definition here. Okay. And there are two important theorems which we are going to use. The first theorem is that universal property of quotient maps. This is the typically that theorem which actually help us to solve this kind of problems. Okay. So this theorem tells as follows. Suppose we have a quotient map L s to x, and we have some map. That means, let me write it down. We have some map f x to y, and we have the quotient map L x to x. Then we will get a map from y to f such that this following diagram commutes. Okay. So that is the thing. So that is what written in the theorem. Okay. And the third theorem is that under certain conditions, closed map becomes quotient map. So that is to say, we have a continuous bijection f x to y from a compact topological space x to a Hausdorff space. That is, domain is compact, codomain is a Hausdorff. In that case, we can directly say that y is the homeomorphism. Not only that, as well as the quotient map. Okay. So these are the three theorems which we are going to use now. Okay. So now let's see the solution of the problem. See, what we basically need, we need to define a map f from x to some space such that that map becomes a quotient map, and x quotiented by tilde becomes a homeomorphism. Okay. So I am displaying that same thing here. So we are starting with S2. Okay. And x equal to s by tilde. Okay. So now the map which we are giving is the following: f x to plus minus 1. I mean, sorry, close to minus 1 to plus 1. We are sending only the third coordinate. Okay. Now there are few things we need to check. One is well defined. This is one thing. Second thing is injective. Third is surjective. So how the well defined is coming? If P is equal to Q, that obviously P3 equal to Q3. So there is nothing to check. I mean, it is a well defined, obviously. So there is nothing to do. Okay. And if Fp is equal to Fq, that implies P is equal to P3 is equal to Q3, which tells P is equal to Q. So that tells third bracket P is equal to third bracket Q. So it is surjective also. Okay. Sorry, injective. And for surjectivity, what we're taking? We can take for any c minus 1 to 1. If we take this point root over 1 minus c square comma 0 comma c, then f of p is equal to c. So this tells that if the bijection, okay. So we are constructing a map f from x to minus 1 to plus 1, which is bijective. Now what we need to show? We need to show it's a homeomorphism. For homeomorphism, we shall use theorem 2, and we shall show that it's a homeomorphism that is left, that is capital X compact and minus one Hausdorff. If we are able to show that, then it will be homeomorphism. Okay, so now let me show the second part of the solution. First thing is that f is continuous, we need to show. The point is that we are first consider projection map from, actually it is a sphere, that is third corner projection. It is the obviously it is continuous, so it is continuous, which is obvious, so there is nothing to explain. Okay, now we are going to use the theorem 1. This is theorem 1 by which we are using this diagram P3 is equal to F compose tilde, and this is the universal property which we are using, and that tells that P3 is continuous and F is F, so that implies the F is continuous, and by theorem 1. Okay, so there is nothing to explain. That is x, we are first defining map x to minus 1 to 1, and then we are getting a map from x to x, that is sorry, that is what, that is quotient map, and x to f, this is f, our map, and this is p3, and this diagonal commutes. And so this tells that theorem 1 tells little f continuous, so there is nothing to explain much. Okay, so the continuity is over. Now there's a homeomorphism to show. Sphere is compact and minus 1 to 1, that is a Hausdorff. So these things are very common things, so that is no, I mean there is no point to explain this. And x is equal to L of S, so it continues with compact with compact. So f is a map from x to minus 1 comma 1, which is continuous bijection from a compact space to a Hausdorff space. So by theorem 2, it will be a homeomorphism. Okay, so that is the argument. So finally, what we get? The quotient of this x is homeomorphic to minus 1 comma 1. Options. So option A is clearly the answer, 1 comma plus 1 under the usual topology. Okay. Now suppose B is correct. That means, I mean, if any of the B, C is correct, that means these spaces, these house spaces, this circle or this disk or this cylinder, those are homeomorphic to the interval minus 1 comma plus 1. Okay, but the point is that if you let me write it down. So if you take any point from inside, and suppose we have some homeomorphism G, it will have a pre-image here CD, such that GC is equal to D. Okay, but circle minus a point, it's connected, but minus 1 comma 1 minus a point, it is disconnected. So this implies option B not true. Okay, and a similar connectedness argument also tells that option C and option D are not correct. So only option A is a correct answer. So that is the whole argument for this question. Thank you.